Swayam Prabha, free DTH channel for education.
Hi students, welcome back to the online video lectures of the medical imaging course. In this video lecture and perhaps the next couple of video lectures, we would see few aspects of CT image reconstruction. In particular, in this we will start with Radon transform. In the next lecture we would see about Fourier slice theorem and perhaps one more method we'll see in the next lecture after that. Okay, so before we go on to that, let's again look back into how exactly an image is reconstructed by using computed axial tomography, and also normally referred to as CT as well, computed tomography image. If you recollect from X-ray images, what you had there is a 3D object. X-rays are sent from the source and then it gives you a 2D projection. So essentially you are getting a 2D image of a 3D object. The basic idea when it comes to CT image is an extension of this radiography imaging, where instead of just having one 2D projection of a 3D object, suppose if I give you multiple projections of this 3D object from various viewpoints, is it possible to reconstruct the 3D object from multiple 2D projections? That's exactly what CT image achieves, and we will see some of the very basics or fundamentals required to understand and appreciate this mathematics involved and the signal processing involved in CT image reconstruction. What I'll do is just I'll quickly show you how the setup for CT scan would be there. I'm taking few YouTube videos. So this is how the inside of a CT scanner would look like if you remove the cover there. And this is referred, whatever you are seeing on the top, you have an X-ray tube for generation of X-rays, an inverter to give you the required power supply, collimator for focusing the X-ray beams, right? And on exactly on the opposite to your X-ray source, you have a detector. Of course, a data detection system would be there inside it itself, and high voltage multiplier for X-rays, generation of X-rays. And let's take a quick look at another image that shows you, which we would normally won't see unless the upper cap is removed. This is how it keeps rotating. Yes, it rotates at such a high speed. Okay, but they make sure to minimize the noise that you would get with all the enclosures and other stuff, but this is how it rotates. So let me come back to the presentation. So what is in fact done here is, at one angle you would be sending the X-rays, and exactly opposite to that you have a screen or X-ray sensor, and both of them would be rotating in the gantry is inside that the patient is there, and you take multiple projections are required and they are combined in order to get the 3D object from multiple 2D reconstruction. So that's the basic idea for CT image reconstruction, and this concept is same even if you go for PET CT, somewhat similar to MRI. Also you have multiple acquisitions you do in order to get 3D. Anyway, we will come back to MR a little later, which is slightly different. So now let's take a look at into the mathematics involved here. Let me move on to a notebook mode to work out these things. For the sake of simplicity, what we will do is we consider a 2D object here for which we are getting 1D projections, so that you could fairly, without much of a problem, you could extend that without loss of generality to 3D case also. Let's consider a 2D image. You consider it as function of xy. You can consider it as an image we have in 2D. Let's say this is your x-axis and this is your y-axis. When you are scaling it down by one dimension, you could think of the equivalent problem when it comes to 2D, as you get multiple projections of it. Let's say a simple case we would consider first. You are taking a projections parallel to the y-axis, okay, and these are all falling on a screen, you call it, or a sensor for that particular kind of rays that you have. And now what it would do on the sensor here, you would be getting a 1D projection of it. Let's say the profile you are getting now is, here is something like this. These are the values that you are getting, let's say. Okay, now another scenario is, now for example you are taking multiple projections. So assume that now you are taking it a different angle here, the same object, and you have a screen here now, or a sensor here, on which you are taking projections of it. As you are taking projections, it is essentially an integration of all values here that are there on this part, and then you are getting, let's say, another profile here, okay, with this across this angle. Okay, this you could repeat this whole experiment in different ways. For example, if you want, I'll draw one more. You are taking now in this direction, and you have a sensor here on which you are taking that, and that may be, let's say, you are getting this sensor here. So given these multiple 1D projections, how could you get f of xy there? That's the problem. In this case, a simple case from 2D to 1D we considered. Similarly, you could think of from 3D to 2D. So how do you solve that? That's the question here. As a first step towards that, assume that this sensor is there at an angle theta with the x-axis, and if I know that this function is f of xy, let's call this, as this way is varying with respect to theta, let me call this as x prime. How can I express g theta of x dash with respect to f of xy? Once you understand how g theta of x dash is related to f of xy, the rest of the things we could further continue. So let me for this purpose draw things again here with just one projection. Again here, for the sake of simplicity, let me take first a projection along the y-axis. Okay, this is your x, assume that this is your y-axis. I am taking a projection here where you are sending the rays in this direction, and now assume that this is, so in this case this is nicely same as this x-axis here. Now the question is, let me call this as function of x comma y. Now if you are projecting in parallel to the y-axis here, what you have here is a function of x. Now how do you express this function is related to f of xy? You pause the video here, try to work out. This is a very simple problem. Try to work out this, and then you continue with this video. Right. So now you could see here the value which you are getting here is an integration of all the values. So for example, in case of CT, you have different objects within the, let's say, the brain or the head for which you are taking CT. So this is equivalent to the integration of all values of absorption coefficients that are on the way to this ray. That's exactly what would give you this g of x. So that's absorption coefficient in case of a CT image. This would give you absorption coefficient, and these in that case would be your x-rays, and this would be your detector here. And for example, this could be any your object of interest for which you are trying to compute the 3D profile, in our simplified version here the 2D profile from 1D profile, right? So this is accumulation of all absorption coefficients of all voxels that are falling here. So how could I express my g of x here? So g of x would be equivalent to, I am integrating along the y-axis, you could see here the x value is constant here. When I am getting its value here, you are integrating for all values of y from plus infinity to minus infinity, or I could write minus infinity to plus infinity, and f of x comma y, and for all values of y you are doing, so this is y varying from minus infinity to plus infinity. What we will do now is to generalize this angle at which we are projecting these parallel lines to some angle theta, right? Let's draw that out for clarity. This is your x-axis, this is your y-axis. Assume that I am projecting them in this direction, okay, and that is giving me some profile here. Let me call this angle as x prime, and this line making an angle of theta with respect to the x-axis. This profile, as it is dependent on theta, let me call it as g subscript theta. It is dependent on a single parameter now, x prime, so g theta of x prime. Now the question boils down to, how could I express g theta of x prime in terms of f of xy? If your projection is perpendicular to your, let's say, x-axis, the case is pretty simple. You could notice here, suppose instead of this f of xy, if I rotate this coordinate axis by an angle theta, okay, so assume that this is my new x prime and this is y prime, okay, where I am rotating here by the same angle theta, and if I express this in terms of f of x prime comma y prime, now the rotated original function, then this is pretty straightforward. Then I could write g theta of x prime as y prime varying from minus infinity to plus infinity, some function of, okay, xy in terms of x prime and y prime. So for the time being, let me call it as some other function h of x prime comma y prime into dy prime, okay, the newly written function. This will not be right straight away, so let's call this as some h of x prime comma y prime. So then you just take across y prime from minus infinity to plus infinity, you take any line here and you integrate all those values here, that would give you this value. That's how you would get that. So for that, what we need to do now is simply do a, what would, for a given xy value, what would be its, if you rotate your coordinate axis, what would be the, and assume that I give you that I rotated by theta, and the new values be x prime and y prime. How can you express them in terms of x comma y? That's the simple problem that we are now going to address. So x-axis, you have y-axis, you have now rotated them by an angle theta, okay, I'll assume that are at one point here, and now consider that you have a point here whose coordinates are x comma y, and after you do this transformation, let those coordinates be x prime comma y prime. How are they related to each other? This is what we are going to work out now. You could see now geometrically that if I just drop here, this is equal to x, and if I draw a perpendicular here, then this would be equal to theta, and this is equal to x prime, right? Intersection from a line which is parallel to y prime. This is your y prime, right? If you are drawing that, then obviously that would give you x prime, and so that's essentially exactly equivalent. If you want me to draw here, that's exactly equal to this, and then of course this is equivalent to y prime. What about y? You drop it here, okay, and this would be equivalent to, then this would be, of course this is x, whatever I have drawn here is x, that we anyway marked here, but this would be equal to y, this value would be equal to y, right? And what else? Of course, if I draw a line here, okay, and this distance now you let me draw a dotted line here, also drawing perpendicular here. Now let's try to write the expression for x in terms of x prime, y prime and theta. So x, so this being equivalent to x prime, right, the whole line, theta, so this would be equal to x prime cos theta. And what about this? This would be equal to, look here, this is the diagonal of this right angular triangle, and so this would be equal to y prime sine theta, correct? So your x is equal to x prime cos theta minus y prime sine theta. Now similarly, let's write expression for y. Y would be, this is the y value here, and y would be, if you take x prime is here, so this whole length is you want this whole length, right? And this would be, where is your x prime? Yeah, this is your x prime. So what would be this length here? You look at this length, right? This being x prime, right? That length is exactly equivalent to this length, of course, and this would be equal to x prime sine theta, right? And to that you want to add this value. This is equal to, where is y here? This is your y here, so this is equal to y prime cos theta, this value. So this is equal to x prime sine theta plus y prime cos theta. If you want, we could write it in the matrix form. If you have rotated by an angle theta anti-clockwise, then this x comma y is equivalent to cos theta minus sine theta cos theta times x prime y prime, isn't it? If you want, I could write it as the matrix form. This, let's say capital X is equal to, let me call this matrix as A, this matrix as x prime, okay, capital X prime I am writing. This is the relation. So now if you give me this x prime, the new ones, I could tell you the old ones. If you want the other way around, if you want to express x prime, how is this related to x? If you want to write it, how do you simplify this matrix equation? You have x equal to a times x prime, you multiply here on both sides, on the left hand side by a inverse. This is a unity matrix, identity matrix. So what you have then is x prime is equal to a inverse times x. Of course you could do that geometrically as well, but I am just doing here from the matrix operations. So what is the a inverse here? A inverse is it's a 2D 2 by 2 matrix, 1 by AD minus BC into D minus B minus CA. The 1 by, the determinant is cos square theta plus sin square theta, it's 1. Then interchange the values of this and this, that would remain same. So cos theta, and then change the signs here, so that would bring sin theta minus sin theta. That's your A inverse. In other words, I could then write, for example, my so x inverse is equal to cos theta sin theta minus sin theta cos theta times x. That's the relation. And of course, if you want, you write them as smaller x dash. So you write it in terms of each x and y there. X dash equal to x cos theta plus y sin theta, and y dash equal to minus x sin theta plus y cos theta. Hope this is clear. Now let's come back here now. This equation, to come back to this equation now, how do you express this? Okay, f of xy, how could I write it now? My f of, I use the same thing here. Now my f of x comma y is equivalent to x. I could substitute these values there when I am rotating by theta. So x dash y dash are obtained by rotating it by an angle theta. So x dash cos the f of x dash cos theta minus y dash sin theta comma x dash sin theta plus y dash cos theta. That's your f of xy. Okay, in terms of x dash and y dash. That's, in fact, if you want, this is the h of x dash comma y dash that we are talking about here. Right. Now let's write g theta of x dash now, the expression for it. G theta of x dash is equal to, you vary y dash from minus infinity to plus infinity, and h of x dash y dash, so there let me write it as f of x dash cos theta minus y dash sin theta, and x dash sin theta plus y dash cos theta, right? And you do the integration with respect to dy dash. That's it. This would give you the profile of g theta of x dash given your f of x comma y. Okay, and this, there is an important name to this. This is a very popular transformation, and this is referred to as Radon transform. Okay, I hope what we have discussed is clear to you. Let me quickly recap what we discussed so far. We just mentioned that in CT, if your object is 3D, you take multiple 2D projections of that object and you combine them appropriately, multiple 2D projections, in order to get the 3D profile. We have not yet discussed about how you combine them in order to get 3D, but all we discussed in this class so far is, if I tell you at what angle I am parallelly projecting my X-rays and putting my sensor at an angle theta, what would be the values that I would get on this projection? So of course we went one dimension down for the sake of writing them in a convenient way. We took a 2D object and took a 1D projection. We have worked out the mathematical expression that tells you, if I give you an angle at which I am projecting my X-rays, and what would be the resulting 1D projection of that 2D object. That's what we discussed in this class. We'll continue this in the next video lecture. Thanks for watching. See you in the next video lecture. Bye. Take care.